And good evening, everybody, and welcome to the Sigma monthly meeting for October, where tonight we'll be looking into the causes of astronomical dimming. For those of you who don't know me, my name is Pete Sherman, and I'm the chairman of Sigma, and I'll be your MC for this evening's proceedings. With me as helping in the background is Rich Oakley, who is the Zoom co-host, who will take over should anything go wrong. So you probably won't see him unless I have an issue here, which the way tonight's been going could possibly happen tonight, but we've got a backup, so don't worry. Also with me tonight is Stuart Brooks, who will be doing Space News. We've got Mick O'Donnell, he'll be doing the Moray Sky at night, and Donna Williamson, who will be handling the Q&As throughout the talk. Now, a little bit different here. If you, we normally leave all the questions and answers to the end of the talk, but Hugh tonight said he's quite happy to take questions in the talk. So if you put them into the Q&A, which I'll show you how to do in a moment, Donna will handle them. And if Donna has any issues, Richard will step in again. So with that, I'll just go through the Zoom controls to show you how you can ask your questions and do a few other things. Okay, the first thing you'll see down here is audio settings. Okay. Now you can use this later on because I say we're having that gathering later, which I'll tell you about in a moment. If you actually click into this up arrow, you can test your speakers. Later on in the gathering, the Sigma members gathering, you will have another option in there to test your microphone as well, so you can test that before you come in or while you're in there. Okay, but if you happen to be watching this on a big widescreen TV or something like that, you can choose which speakers you want the sound going to. That's a little handy tip for you in that toolbar. Okay, the next thing we have is the chat. A few of you found it already, but what you can do is you click this button here, the chat button, you get this pop-up panel come on the side. The default is set to all panelists. If you actually type anything in there, it will just come through to myself, Rich, Hugh, Stuart, Donna, and Mick. Okay. What you need to do is to click the little down arrow this time and change it to all panelists. Oh, sorry, that shouldn't have happened. To all panelists and attendees, and then you can chat to everyone in the room and say hello. Okay, to ask your questions, the way we do it in the Zoom webinar meeting is to click this button here, which is the Q&A button. You get this pop-up panel come up. Nice and simple, type your question into there and then press the send button. I say Donna will keep an eye onto that and say she'll ask them throughout Hugh's talk at an opportune moment. Next thing you have, if you have any issues at all and you want to get a hold of us, any of us on the panel, you can actually click the raise hand button, which I say is just here. When you click that, it will turn green. We will see your hands up, we'll see there's an issue, and we'll contact you through the chat and ask you what your problem is. Okay. Another little thing you can do is just here. If you click the view options button at the top, sometimes at the bottom if it's on Apple, I think, you can change your screen ratio by using these percentages on the side. Okay, if it isn't looking quite right, click into one of them and see how it's looking. If it all goes pear-shaped and doesn't look right, just click fit to window, which is the default, and it'll go back to that stage. And I think sometimes you've got a little bar on here as well that you can drag left and right that will actually make this presentation screen bigger or smaller and the speaker bigger or smaller. And the final thing to remember is at the end of this meeting, don't go too soon because we will be putting the link to the members gathering where we can all get in and have a chat later on. But when you've got that link, my mouse is playing up again, I don't know why. Once you've got that link, then just click the leave button there and go to the next meeting. All right. So I'll stop my share and you can have me in big screen. Hi, how's everyone doing? Okay, one little thing, if you were using your phone or anything to actually watch this on, or a laptop or anything like that, make sure it's plugged in because Zoom is a very, very power zapping program and you'll probably cut out halfway through Hugh's talk. Okay, right. Yep, as I say, we're going to have a members gathering later on. Okay, now we're going to try this. This is the first one we tried. So at the end of this, Richard's going to pop up the link to the next meeting. You should all have it in the newsletter anyway, but any visitors here, you're quite welcome to come along as well. All you have to do is to, let's say, copy and paste the link, or just, it should be a clickable link from the chat. So click that link, you'll go over to a waiting room, and then, as I say, wait there. We got to close this meeting down to open the other one, and then we'll let you in. But more about that a little bit later on. Okay, just the meeting brief then. So the way it sort of works for those of you who haven't been to a Sigma meeting before, we have a main talk, which is started by Hugh Hudson. So Donna will be handling the Q&As during and after his talk. Okay, we then have a little 10-minute break. Okay, not many sort of Zoom meetings have a break, but we need a bit of a break because we've been here about 6:30 getting this set up. Okay. Then after the break, Stuart comes on. He will give us a space news. Mick will then be giving us the morning sky at night and show us what we can look at in the nighttime sky. And there'll be a little bit of club news from, from myself. Okay, and that will be about the end. We'll look at finish about 9:30, 9:45. But that's it. Anyway, on to tonight's main speaker. Now, I've done my usual Google search for our speakers to give a little bit of an intro. Now, Hugh, there's not a lot on the internet about Hugh, unless I didn't dig deep enough. So I dug a little bit deeper, and did come up with Hugh Hudson, who was a British film director of The Chariots of Fire, and I thought, well, that's not him, so I'd better dig a bit deeper again. But as I say, it gives me great pleasure to welcome back to Sigma. He was here a few years back, all the way from Glasgow University, Dr. Hugh Hudson. I must thank him for giving up his time to put this presentation together and come and join us tonight. Hugh is an honorary research fellow at the School of Physics and Astronomy at Glasgow University, and a research physicist at the University of California, Berkeley. Hugh Hudson was the Eclipse mega movie chief scientist at Berkeley. Now, if you've not seen the mega movie project film, I would suggest you go and do it. It was a collaboration of more than 1,000 amateur astronomers and avid photographers to record the 21st of August 2017 total solar eclipse and upload the photos and stitch them together to make a movie documenting the path of totality from landfall in Oregon until the moon's shadow slipped into the Atlantic Ocean off South Carolina. I had a look at it last night, and it is something pretty stunning. Okay, you can find it on YouTube, nice and easy to find. I'm going to put a link to it later on. So everyone, Hugh, if you'd like to turn your video on, you're quite welcome. Would everyone please give Hugh a warm welcome? I'm hoping he's here.
Here, I'm here. Shall I share screen?
You can share your screen, and away you go, Hugh.
Okay. Okay, you should have it now. Is that?
You just need to go
full screen.
Your full slideshow.
Right.
There we go. You're in. Over to you, Hugh.
Okay. Well, thank you, Pete, and I'd like to thank you and Sigma for, in spite of the fact that I was up there before giving a talk, inviting me again. And it's a pleasure. It's especially for me, it's a pleasure to talk about this topic. Excuse me, because of the experience I had with the eclipse in 2017, and just to remind people, there is another big eclipse coming in 2024. I'm not sure what my role will be there, but in any case, it will involve dimming because the sun will be eclipsed and will get dim. Okay, so dimming in general is the topic here, and so I would like to talk about things that the absence of things giving astronomers information about something. And of course, the most extreme example of this is the eclipse, the total eclipse of the sun. So the synopsis here is that astronomers can learn from things that they cannot easily see by one means or another. And I should say the literary inspiration here is from Sherlock Holmes. I don't know which story this was, but in one story, one of the major hints, clues that enabled him to solve the crime was the fact that the dog did not bark. So this is a sort of a crude analogy of something the astronomers cannot see, but from which they can actually learn something useful. And my list here of things ends in Betelgeuse, and so I would appreciate it. This is the most exciting part of this. So I would appreciate a warning 10 minutes before the end of my allotted time so I can skip anything that I have dwelt too long upon, so I can get to Betelgeuse. Okay, so the first item, we start with sunspots. Sunspots are dead black, right? So there's nothing there that you can see. And the reason you cannot see anything there really is because the sun is so bright. If you took the sun away but left the sunspot, it would be extremely bright. You would see structure in it, and it would be very nice. But for all practical purposes, because the sun is so bright, and because the sunspot is so faint relative to that surface brightness of the sun, it is just a clearly defined black area on the sun. And this is the view that Carrington had. Carrington was one of these great semi-amateur, semi-professional, rich, self-funded kind of scholars in the 19th century in Britain. And he had his observatory, and he contributed enormously in several areas. One of the ways he contributed was to make sketches, very careful sketches of sunspots, and this is one of them. And it was published recently by Sean Prosser, named down there as who's the secretary at the the librarian at the Royal Astronomical Society. And so I thank her for putting this up for us. And the color you will see is exactly the color of Carrington's projection screen. So he observed the sun by projecting onto a screen, and he had a very ingenious system of fiducial wires, so that as the sun with Earth rotation drifted across these wires, he could make precise timing. And the information he got about sunspot positions was extremely valuable. And it also led accidentally to what I'll talk about next. Accidentally, after he finished sketching this very, very large sunspot group here. Can people see my pointer? I hear nobody saying yes.
Yeah, perfect, Hugh.
Okay, so I'm running the pointer around this big sunspot group, and just as he had finished marking it off and sketching it like this on his projection screen, which was, he described the color of this is a pale, I think a pale distemper of straw. So it's a straw-colored sun, not far from the truth, maybe. So just at the end, a flare happened. So this is a very famous story. This on the right is the same sketch, I think somewhat redrawn, but illustrating with these four areas here, A, B, C, and D, where this flare appeared. This was the first time somebody had actually observed a flare, and the observation was made by this very competent astronomer, Richard Carrington, and it was confirmed by a friend of his down the street, in the next county, probably, Hodgson. And so this is a real thing. And of course, since it hadn't been observed before, it was very good that there was a confirmation by an independent observer. So what Carrington saw was very bright, and Hodgson, the other observer, said this is a kind of bluish, it's kind of like Alpha Lyrae, very intense, perhaps it doubled the brightness of the sun locally in these patches. So this is what we call a white light flare now, and it moved, right, between A and B, it moved to C and D, across pretty much the whole width of this sunspot group in about 5 minutes. And it appeared in the west. As you can see up here, he's using the solar astronomers' coordinate system, which is north and south, but then preceding and following. So preceding in the sense of solar rotation, the sunspot's drifting from east to west. So preceding in the west. All right, so that's the discovery that was made because there was nothing there in the sunspot, but all of a sudden something happened. The message here is that this careful study of nothing led to this great accidental discovery, the first solar flare, and then what we call space weather. And I'll talk about that a little bit further down into the presentation. Right, so this will occult the sun a different way now. And you can see on this image of the sun, which I grabbed from the internet, don't know whose it was, but you can see this amazing airplane flying across it. I'm pretty sure this is an MD-11, but maybe somebody who knows airplanes can correct me on that. in any case, there it is, you know, its image projected against the sun, and it's very dark. And of course, the sunspot has a few sunspots here and there. And so that's clear evidence of the Carrington kind of thing. There's one tiny one down there. But this big black thing is Venus. So this was in 2012. And so this occultation of the sun or the transit of Venus across the face of the sun is something that doesn't happen very often, but it's quite interesting that it does do that. And so, as you will recall in the annals of history, it was Captain Cook was sent to the South Pacific to observe such a transit. They don't happen more than twice in a lifetime, but in 2012 there it was. And you can see it's a pretty big fat planet. And the sun is pretty big, but the Venus is subtending a substantial fraction of it there. And as Venus got to the limb of the sun, you can see very sharply defined, a very black gouge taken out. And the reason that I think this is interesting from an astronomer's point of view is that this is really black. It is a foreground object which is concealing the sun itself, and so there is no scattered light. If your telescope has scattered light, it will be the only source of brightness that's inside this shadow. And so it's the bane of the solar astronomer is controlling scattered light, because optics are dirty and the sun is bright. And so one always gets a halo of scattered light, which is a nuisance. This is a very good way to control that if you make an observation of this sort. Okay, so now here's the official NASA movie of this. And it has a very boring soundtrack. I hope it's not too bright, too loud. And here comes Venus in visible light. This movie is quite nice. It's freely available because it shows you the transit in many, many wavelengths. Here comes an ultraviolet, extreme ultraviolet wavelength, and here, in different wavelengths, you can see a very funny thing happening. You see all kinds of structure on the sun. That's the helium-304, almost here. There's a white light again. You can see all this stuff. Okay, so I think oh, that was noisy. I think I'll stop there and just call your attention to this kind of artifact that I noticed. If you go back and forth across in one of these ultraviolet wavelengths, let me move it back and look very closely, you'll see brightness inside the disk of Venus. All right, it shouldn't be there. It's a structure. You can see the limb of the sun there. At least I can see it. Here, right there. Okay, so I think what's happening there is that this is an MPEG, so it's a very crummy format in which the individual frames of the movie are linked together, and so it is doing a smoothing process to make a smooth movie out of snapshots, and in so doing, it's mixing the images. So I suspect that's what's going on. In any case. All right, so that's showing you the transit in progress. And
excuse me, Hugh.
Yes.
We've got a quick question. Eric Walker is asking which cameras and space probes are being used to capture the images in that video. Right.
That is basically SOHO. Oh, sorry, SDO, the Solar Dynamics Observatory, and its instruments are the in white light. It was the HMI, the Helios. These acronyms always confuse me. HMI is the oh no, it's a magnetic imager. Anyway, it's what measure. It's the magnetic field measurement, and the beautiful colors in the ultra helioseismic and magnetic imager, and the colored images in the extreme ultraviolet are from the Astronomical sorry, the extreme ultraviolet imaging, it's AIA. And so anyway, it's all SDO. And SDO is still out there churning the data out at a great rate. It's in geosynchronous orbit. And so it has continuous solar viewing, just about, only narrow periods of eclipse. And it's just a wonderful, wonderful tool.
Okay, and another quick question. Rich is asking, what did Venus's transit of the sun reveal about Venus?
Right. Well, that's another excellent question. It revealed clear views of the atmosphere of Venus, actually, because you can see the knife edge of this. I think you cannot see it in that movie, but careful analysis actually shows you the structure of the atmosphere a little bit. So I think that's the basic novelty of it. Otherwise, it is just a tool. And of course, from the point of view of Captain Cook and astrometry, the timing of the eclipse of the transit is extremely precise and very important for the structure of the solar system and for things like the relativistic corrections to the dynamics of the solar system. So, and as a non-expert on Venus, I think that's about the limit of my knowledge.
Okay, and obviously while we're asking questions anyway, Bill's asking, once Venus is clear of the sun, can you see any light scattered through the atmosphere into the dark side?
Of
well, Venus?
No, well, Venus has a crescent, right? As it gets into the greater elongation, it starts to develop a crescent. Is that what you mean? So you're starting to see the illuminated, a bit of the illuminated side, but that takes a couple of days to develop properly.
Okay. I'm sure he'll ask again if there was any more detail he needs on that. So thank you. That's all the ones that popped in just now. Okay, and I will point out that in very nice pictures of the solar total eclipses, like the ones made by our Czech friend, you can see in a proper exposure, you can see the moon in front of the sun. The corona is faint enough so that it's possible to make a compound image or even a single image, which shows you something about the moon as it's being illuminated by Earthlight. So as the moon is passing in front of the sun, of course the Earth is behind it, and the Earth is being illuminated fully by the sun, and so there's Earth shine on the moon, and you can see it. In the case of Venus, I think it's so far from anywhere else as a source of light that disk is really black, much blacker than the total eclipse disk you see for the moon. Okay, and so this graphic here shows you the time series, time development of the brightness being measured by an instrument on, I think, its own satellite called the ACRIMSat. This is the total solar irradiance. It's a bolometric measurement of the total sunlight expressed here in MKS units, watts per square meter. And over here on the right, it's in fractions. And you can see that it's very nice over a period of 8 or 10 hours, the transit happens. And you can see this dip here caused by that transit. And the dip has about a 0.1% extinction of the sun. So it's not a very large effect. Of course, on this scale, the zero of this scale is down in the basement somewhere. So this is a very, very precise measurement of the solar irradiance with a fluctuation of only, you can express this in terms of parts per million. And then the eclipse happens. And you can see the model here, this blue line is kind of wavy. And the reason for that is that over these 8 or 10 hours, over these 8 or 10 hours, there is orbital motion on the satellite that's making the measurements. It's in low Earth orbit. And so its orbital period is about an hour and a half. And so every hour and a half, it's rushing towards the sun or rushing away from the sun. These bands here are where it's eclipsed. Observing satellite is eclipsed, no data. And so this wavy line is the consequence of that. Okay, so this is this possibility leads immediately to the idea of discovering exoplanets by transits. And this is another dimming kind of thing. This turns out in 2012, by 2012 already, the Kepler spacecraft was up there doing this kind of work systematically, and they discovered with Kepler, and are now discovering further with new satellites, TESS and Cheops. People are discovering exoplanets left, right, and center. There are hundreds of them by now. And one can ask the question, we could ask it as soon as we started to see this TSI observation and these fluctuations. You can see in the before the transit and after the transit, there's a signal fluctuating up and down. We could ask the question, what is the minimum detectable exoplanet that you could find by this eclipsing technique? And so this is, I think, a very interesting, back of the envelope kind of sort of thing that an astrophysicist might think about, or you might think about, anybody might think about. What limits one's ability to see planets? So what's the minimum size planet that one could see by this technique? And the reason it's interesting is because there are several variables here. How big is the planet? Of course, the bigger, the easier. If it's Earth or Venus size, it's these planets. Our planet has got a radius which is about 1% of the solar radius. In the case of Jupiter, it's about 10%. And so in the case of the occultation, you square that, so it's 0.01% dimming, or for Earth, or it's 1% dimming for Jupiter. You see, it's easier to see Jupiters, and but that's not the whole story. Also, one has to ask, how often does it occult? So you have to wait for 1 year if it's Earth around a sun. Then it comes back and you see a dimming 1 year later. Well, that's tricky because you don't know it's a year. You don't know where the planet is. So that's a consideration. And for how long does it eclipse? Well, it turns out that it's about 12 hours for the Earth around the sun. So a sun-like star with an Earth-like planet would have an eclipse that would last sort of like this here, but for about 12 hours. Okay, so the main thing though is how noisy is the background stellar variability? Because you can see that if this dip weren't so large, it would be concealed by these fluctuations that are ceaselessly going on. And every star has got variability. There's no such thing as a non-variable star if you look hard enough. And in the case of the sun, the variability is expressed without something going on like this in terms of parts per million. So it's actually quite small, but it's there. And so if the planet doesn't exceed that fluctuation, then you're not going to see it easily. So anyway, put it all together, take all those things, take your envelope and scribble them down in a stubby pencil, and then bula bula blanco, it's Earth. So the minimum detectable planet by the exoplanet occultation detection technique is basically roughly Earth, and Venus demonstrates that. We saw that there. And so I think this is kind of a coincidence, a physics coincidence that's analogous to the coincidence, as strange as the coincidence that the angular diameter of the moon is very close to that of the sun. And so one can have a total eclipse. And all these other variables put together, and there we have the Earth being exactly the minimum detectable planet. And I think that these space missions, Kepler and TESS, are actually discovering Earth-sized planets with difficulty, but it's possible. All right, so that is a comment about that kind of dimming. Right, so here's Kepler looking at a star, looking at an Earth-like star, a sun-like star. Down here, it's going up and down over a period of tens of days. You can see the star rotating this way. It's called gyrochronology. It's going up and down because there's a big sunspot, or there's a collection of sunspots on the star spots. And so it's modulating the signal, the brightness of the star, and in this case by plus or minus a couple of percent. So it's a very large fluctuation, much larger than the sun would show. And it's interesting because, exciting because in this case, this solar type star is making flares. It's making a dozen flares. You can see the brightest one here that's blown up on this inset here. And you can see a whole bunch of fainter ones. In fact, if you look at this time series, it's basically a sine wave plus excursions above and not below. So this is already extremely interesting, because if you look at the sun, and kind of in the analogous way with this total solar irradiance measurement, the bolometric magnitude, you get something like this. This is the first, kind of first moment we had data like this 30 years ago. And you can see that the sun is varying by fractions of a percent, very small fractions of a percent, plus or minus. This whole range here is like well, you can see it on the scale here. It's like plus or minus 0.05. And on top of that, there's a slow, chaotic kind of oscillation, variation, not very systematic. Plus there are these dips, these big dips here, here, and here, very clearly distinguished. And those dips are easily identified if you have an image of the sun, because there's a big fat sunspot on the disk at this time. So this is a dimming that's produced by a sunspot, just like the occultation, like the transit of Venus produced that dimming that allowed us to see its transit. So why is this interesting? It is because of the remarkable differences. This solar type star that I showed you initially, it has flares, positive excursions. It has large variations. It has this sinusoidal pattern of variability. The sun, which is also of solar type, has just the opposite. It's got dips, not positive but negative excursions. It's got weak variability, and it has no obvious pattern to it. So this is the what I would consider flariness versus dippiness. Stars of different types, even in the solar category, in G and K stars, slowly rotating solar type stars, they can be flary or they can be dippy, depending upon how big the sunspots are, or star spots, or other factors. And we don't understand this. This is what I regard as a cutting edge kind of topic. I'm not an expert on Betelgeuse. I'll talk about that later, but I am an expert on this, and I'll tell you that it's a puzzle. We don't know why rapidly rotating stars are much flarier, and slower rotating stars are much dippier. Okay, so this is just the story. I think I have said that, but now I'll ask a question. Based upon this, is the difference between this star spot behavior and sunspot behavior due to the presence of faculae? So I think you all probably know about faculae. Faculae are the opposite of maculae. Maculae at faculae, maculae are sunspots. This is astronomical lore from the 17th century. And faculae are faint, bright things that also were discovered back then, not by Galileo, but possibly by Hevelius. But I think if people with small telescopes can see them, and these are his sketches. Hevelius was a Polish astronomer from Danzig, from Gdansk now, and probably in spite of the cloudy weather that's probably prevails there, he was able to see near sunspots, wispy, bright things, especially towards the limb of the sun. And nowadays, we've got beautiful images from space even, and you can do this from the ground as well. This is from, again, from SDO. This is again from this HMI instrument. And you can see the wee sunspots here. You can also see these bright patches here, and these are the faculae. So they're hard to see except towards the limb of the sun. And they're not strikingly concentrated like sunspots are. They're diffuse patches, and they persist for longer than sunspots do. So but they have a very strong effect on the on the total solar irradiance. And in fact, the stars that are dippy are dominated by this faculae signal. So the question is, how could we know if we just saw this sinusoidal variation here of a solar type star out there with no images? How could we know that these variations are being caused by spots and not by faculae? And it turns out there's very little literature on stellar faculae. They certainly exist, and they're certainly important, but they're hard to observe without an image. So the answer to the question, how can we know, is that there are techniques. One technique is, before I get to those things, let me show you this. This is Hevelius's big telescope. It's, believe it or not, it's 46 meters long. So this is a plate scale of a few arc seconds per millimeter. This is a huge focal plane, and this is telescope. I just want you to admire this beautiful engraving here, and look at the very top of the tower there. There's a staff member of the observatory leaning over, adjusting the pulley, and there's other staff members down there pulling on the pulleys, and there's people with a ladder. And I think safety, I mean, it doesn't look like a very safe thing to do, to climb up and operate this telescope, but no doubt it was how Hevelius made some progress in astronomy. And I was quite amazed to learn about him. And so thank you, Sigma, for letting me study this up a little bit. Right, so this is the question about spots and faculae in terms of zebras. Is a zebra basically a white horse with black stripes, or is it a black horse with white stripes, or is it just not even a horse? It is a horse. It's an equus quagga in this case. So the techniques that people have for doing this, one of them, the most interesting one here, is what is called Doppler imaging. So I thought I would explain this to you because it's kind of neat and not obvious at all. So let me try to explain. In fact, I had to think hard about it as I put this slide together. What you see in this line here is line profiles for an absorption line. So you're seeing the absorption line spread in wavelength, and the Doppler shift is contributing to the red or blue sides of this line. So as a spot moves across the face of a star you're looking at, you will get a Doppler shifted line profile. And you can see if the spot is on the right-hand side here, there'll be a little bump in the line profile that corresponds to a receding motion. If this, I'm assuming the star is rotating from left to right. And if the spot is on the left side, it's approaching because the star is rotating from left to right. And there you get a wee bump on the blue side, not the red side. And so that's what's called Doppler imaging, and it's a very powerful technique. This particular sketch was done by Strassmayer to show the magnetic field. So you can use this as a Doppler, it's called Doppler-Zeeman imaging. You can use this to study the magnetic fields of stars and learns all kinds of things. So this is one of the techniques, so you can distinguish stars, rapidly rotating stars with broad absorption lines. You can distinguish spots and faculae quite easily. But even more easily, if you have a transiting planet, as the planet goes across the spot, it will make a dip. And so there clearly what you see in this light curve is large star spots. Okay, so there's Hevelius, there's Quagga, there's Doppler imaging. So if we look at the sun and ask about how big the spots have to be, these are the spots of the Halloween flares of 2003. I don't know if any of you saw the aurora. We saw it very clearly in Glasgow on late October 28th or 29th probably, when these big sunspots were on the disk of the sun. And it was quite an astonishing display. I don't think I've seen the aurora down here since then, actually. But it was nice, and just out the kitchen window, right? So even through the lights of the city. And what I've done here is to plot the areas of these sunspots as a function of time across these 2 weeks of the rotation of the sun that carried them across. And the color blue, red, and dark blue are 3 different sunspot groups. This one, and this one probably. And you add them all up, and you get this big total effective area, which is in solar astronomers' units, 6,000 millionths of the solar hemisphere. That's a unit for you. 6,000 millionths of the solar hemisphere. So that's 0.6%, right? So that's a big dip. And sure enough, if you look at the TSI kind of measurement for that time, there it is. That's the big dip that these sunspots caused. And you can see also that on this time scale, this is 400 days, many rotations of the sun, you don't see any tendency for sinusoidal variations or even return of the spots. So these spots all were greatly diminished by the time the sun rotated 28 days around to come back again. So this is very different, as I pointed out, from the star spot morphology. And the dotted lines here are big flares. These are the times of big flares. So as these spots appeared, and I can tell you I don't know any theory for this at all, but these three spot groups all appeared at the same time in very different places, and there's no reason that they should. So this is another kind of cutting edge science question. How can they all have popped up simultaneously? And all three of them made big flares, and some of these dotted lines come from each one of them. So this is showing you again that you're being taught something by this dimming signature, but you don't know what it's going to tell you. We're still learning about what it actually kind of means. Right, so the message here is what I've just described, dippiness and flariness, and the sun, which is just showing you dips. Okay, so now I want to get on to space weather. Space weather, as I said, this is the source region for these aurorae that we had in across Scotland in 2003. And that's an element of space weather. Space weather, that's a new term to describe what solar flares and coronal mass ejections and solar cosmic rays do. So there are kind of three main ways, three forms of bad news that the sun can produce. One is kind of the electromagnetic pulse, that's the flare itself. And if you saw Ocean's 11, the movie, there was a famous electromagnetic pulse there. But that's not the most harmful thing, is the mass ejection, which could come and derange long transmission lines for electric supply on the surface of the Earth. And cosmic rays, of course, which can do great damage on satellites or to astronauts if they happen to be exposed. So there's three channels of space weather. Only interesting to us now that we get into space, really, but especially interesting because we would suffer on the Earth, human society would suffer in the case that perhaps a flare, a super flare happened on the sun. But certainly on stars, we're seeing these super flares that I showed you examples of. And so any kind of life on these exoplanets or nascent life or even developed life in the face of these space weather threats would have to cope, right? And so this is the topic, it's now called astrobiology, and it's a very exciting topic since we're discovering all of these exoplanets. And we still, of course, have not seen signatures of life, but it's happening. Okay, so the mechanisms of space weather are flares, as I said, and here's one of them, a big fat flare, and here's the sun taken as a soft X-ray image of the sun taken in 2001, a different time. This is before SDO. This is the Yoko satellite. And I don't want to call your attention to this page, Solar Monitor, which is a great place to get up-to-date knowledge or historical knowledge about solar activity over the past 2 or 3 decades. And the current page, the button there today, gives you a whole range of different images of the sun and these different UV and X-ray and optical wavelengths. And of course, you get access to these time series here as well. So, and we're hoping, of course, that we're not going into a Maunder minimum. We who study solar flares are hoping that the activity will pick up as it's supposed to do over the next couple of years. And so this is a good place to look to see it happening. And now it's a movie of a flare, okay? Luckily, it has no sound. And it goes for 8 or 10 hours. There's a time indicator down there. And it shows you loops. Here's the edge of the sun, the limb of the sun. These loops develop. And the movie is a bit jerky because this is being done not from SDO, but from a Earth orbiting satellite, a low Earth orbit. And so there are occultations every 90 minutes. Let me play it again. But at the very beginning, I want you to see the dimming. All right, so look up here in this corner, or in this corner, you can see light. You can see structure and some emission. All right, when the flare happens, it goes away. See how dark it is there. So that is, let's see, can I control this thing? That is a different kind of dimming. It's not a planet occulting. It is mass going away. And so let me try this, start and stop this. Let me go back and forth over this, and you can see before, after, before, after. So that's a clear signature that a part of the corona has been detached from the sun and blown off. And this is what we call the coronal mass ejection. This is one of the gravest channels of space weather. So this is a technique that you're led to by this dimming signature. And interestingly, another channel of space weather is the cosmic rays. So these coronagraph movies show you the cosmic rays arriving. There was that CME that went by very fast. And you can see all the speckle and streaks and things like that. These are actually cosmic ray tracks in the CCD of the detector on the trace satellite that's making, or the SOHO. This is, I think, from SOHO, the Glasgow instrument that's making these images. That's the near field of view. This is the disk of the sun. And the far field of view over here shows you the same CME, but also this same blast of cosmic rays. The cosmic rays are really great. This long, thin streak here is a particular particle that went skimming along the surface of the CCD. And probably, you can see structure here, the ray disappeared and reappeared. This is because of interactions of different sorts of the cosmic ray with the silicon of the CCD. So very interesting process.
Hugh, can I quickly interrupt you?
Sure.
We've got a question, sorry, just taking the screen down, from Eric asking if the dark areas you refer to are actually dark in inverted commas or only in the wavelength being examined.
They're actually dark, and you can see them in any wavelength. And so the wavelength you're seeing in this movie is an EUV wavelength. But the original discovery of this effect actually was in just ordinary white light, Thomson scattering, just the kind of corona you see during an eclipse or with a coronagraph. And initially, these things were called, what were they called? In the 1970s, they were called, I forget, but from day on day, you could see a sector of the corona just disappeared, right? Now with these imaging instruments, especially with X-rays, one can see the structure and the time development of these dimmings. But to be able to see them in white light, this is the Thomson scattering corona. This just is a very direct thing. It's just the proportional to the number of electrons that you have there. So no, this is it's definitely the corona going away, carrying all of its different temperatures with it. That's a good question. Okay, so now you, of course, you want to ask, could we detect stars, stellar CMEs this way? Could we see these dimmings on stellar CMEs? And the hope for that is in this diagram, which I will spend a minute or so explaining to you. This is what I call an iron cascade plot. This is done with the again with SDO data with the EVE instrument, which is a spectroscope, and it's a spectrograph, which is a sun as a star instrument. It's taking the integrated sunlight and it's giving you just one number at every wavelength. So it's a spectrum, and it makes a spectrum every 10 seconds. It's great. And it does it at all these different spectral lines. Lines, for instance, of helium-like iron. An iron, the ion with only 2 electrons. And down here is iron 9. This is an iron atom with about 20 or so electrons. Typically, these lines, iron 9, 10, 11, 12, have low states of ionization, but are still pretty hot. And so not really hot, but pretty hot. And these are showing you the pre-flare corona. And these are all time series, the duration being about 6 hours, and the range here about 20%. So you can see the flare happening in these hot lines, a beautiful flare. But in the cooler but still pretty hot lines, which are the corona, you can see this dimming, this beautiful dimming signature. And it happens in all of these lines. And it's large enough so that if you had a big enough telescope in the ultraviolet in space, you would be able to look at Proxima Centauri or any other solar type star out there. And if it had CMEs, you would see them. So this is an exciting prospect, but unfortunately, putting a telescope in space is not inexpensive. so nobody's really been able to do this well enough to make this detection, but the prospect is there. Okay, so the answer to that question is yes, you could use this technique to see stellar CMEs, and by inference, stellar cosmic rays that would affect the growth of intelligent spiders on exoplanets, that sort of thing. Okay, so I think this is working out about right on the time scale. I've just gotten to Betelgeuse, and I will tell you that I'm not an expert on Betelgeuse, but I've been in contact. Thank you, Sigma, for asking me to do this. So I've been in contact with Ed Guinan and Andrea Dupre, who are the world's leading experts on Betelgeuse. And Betelgeuse has been a lot in the news because of this. This is a time series put together from data obtained by the AAVSO, the Amateur Astronomer Organization, and over a period of many years, right? This is about 7 years. And you can see that Betelgeuse has these, well, first of all, what is Betelgeuse? Betelgeuse is a first magnitude supergiant, red supergiant star. And the reason people are interested in it is because such a star will evolve sooner or later into a supernova. And it's pretty close to the Earth. It's only a few hundred parsecs away. So I don't have the exact number, but it's far enough away so that it's not going to kill us, but it will still be really interesting. And is it going to do it? Well, this is the pattern of its behavior right now. It has these variations on a time scale of some fraction of a year, semi-regular pulsations, right? Which became very deep, very strange earlier this year, late last year, early this year. And this is called the Great Dimming of Betelgeuse. And I've got a couple more graphics on it here. This is more AAVSO data, and you can see U magnitude, V magnitude, and sorry, U, B, and V, and pretty good data. And there's that big dimming, and it's in magnitude units here. So this is almost 2 magnitudes, well, 1.5 magnitudes, so a serious factor of dimming. And here it is, the current epoch over here. So a third version of this is here. And this is gotten from observers in Pennsylvania, actually. I think they're all in Pennsylvania. Ed Guinan, Wasatanek, and Candlewood, and Corona. There are three amateur astronomers, semi-amateur astronomers who are making these observations. And they've made this graphic, and here's the great dimming here. And over here you see it's returned to a normal sort of dimming, pretty much on the same time scale as one would expect. So this is a one-off episode. What does it signify is the question. But in the meanwhile, how well do we see this return to normalcy? We see these black dots here, which are astronomy from the stereo spacecraft. And so I don't know if this is the very first time this has ever been done, but people have used now this heliospheric imager instrument, which is a solar instrument to observe a star field and do time series photometry. And here's an image from that instrument. The sun is off to the left, and here's Betelgeuse, the star. Now, I actually cannot recognize the constellation here from this display, but they've identified it for me. And it's very nice because they have a lot of stellar sources here, and they can use stars in different colors to normalize the photometry, which is an important thing to make color corrections. And put those points on this graph. After doing those color corrections, you can see, yes, it fills it in very nicely. And I think this is really interesting because technically, it wasn't easy for the stereo spacecraft to make this observation. They had to off-point from the normal pointing direction. They had to employ special modes of observation. They did that several times, I think 5 times, you can see there. You know, a great thrash to get the operations working properly. But they did it. And so and in the meanwhile, Andrea Dupre has just published a paper. This is the other great expert, describing Hubble Space Telescope observations of Betelgeuse. So this is really an amazing thing that one of the brightest stars in the sky is being observed by these instruments, these very different instruments, the HST and also stereo. And the sum total of what we find out is quite interesting. So what is happening?
Sorry, Hugh, before you go on to the next slide, can I just quickly ask a question that's popped up?
Yep.
Have there been any previous Betelgeuse great dimmings?
No, this is the dimmest dimming in 150 years. Apparently, I'm told, not being a great expert, that this star was observed carefully by Herschel, and so in the early 19th century, and so he would make magnitude measurements of this star, and it's been closely observed, you know, for 150 years, and this is the dimmest it's got. So that's why it's called the Great Dimming, and it's explanations. I'm coming to possible explanations for it, and of course, we're interested in it because does this portend a supernova is going to happen? Well, haha. Okay, so here's the picture now that people can make, and this is a red supergiant star. It's a very, very large star, and so it is possible actually to image this star. This is a very unusual situation. Normally, stars are star-like, and the sun is, you can make images of the sun because it's close by, but stars are so far away that they're tiny. This is, they say, the equivalent of 4 or 5 pixels across in these images. And you can see in January to December, this appearance of Betelgeuse changed. It became, the bottom half became dark. And so the idea here that's in Andrea's paper is that there's a gigantic, huge cloud of stuff that's been ejected by Betelgeuse, and it's occulting, it's obscuring, it's dimming part of the star. So that's one possibility. The other possibility is just that this star has large-scale convective motions. That's known theoretically, that this atmosphere, this very extended atmosphere of this very large floppy star has cells, bright and dark convection cells like the sun has, but the sun has tiny cells. The granulation that you can see, or the supergranulation, the convection cells on this object are huge, and this could be one of them. This is again a kind of a theoretical conjecture. So the two conjectures are, first of all, that this is an artifact of the pulsation of the star, some large-scale convective distortion of the star, and the other is that the star has just belched out some stuff that's occulting it. So if either way, you would get a similar effect. And between my two experts here, Ed Queenan prefers the pulsation theory, and Andrea Dupre prefers the exo-CME theory. But if it does come from this pulsation, then one can imagine that something about the dynamics of the body of the star could lead it to an instability, the instability that would create the supernova. So what would happen if there were a supernova? Here on this graphic that I just found accidentally, here's Betelgeuse. And here's the full moon up here in terms of brightness. And the absolute magnitude of a supernova turns out to be about -19. The absolute magnitude of Betelgeuse is about -5.5. So this is a easy calculation. You can just ask what the difference is. It's 13 magnitudes. And so if Betelgeuse did become a supernova, it's reliably going to be within this blue band, probably at the top of it. And so it would be there for 100 days. So this would be great fun if it happened. We'd all be thrilled. And so I'm rooting for this pulsation theory as opposed to this exo-CME theory, but we really don't know. And it's up to the star to tell us, I hope, in our lifetimes. So I've already said these things. It might or might not, this great dimming might or might not portend a supernova, since it is a singular variation, something that has not happened in 200 years. It has certainly got people interested in the possibility, but again, theory lags observation. It has to in this particular case. So I'm finished. I have a postscript, but I'd like to just conclude by saying that it's possible to learn a lot from dimmings, and I have just touched on a few of them. I haven't, for instance, I haven't talked about solar eclipses, which is a very favorite kind of thing. And I would like to thank Sigma for the opportunity, because it's always fun to go into the literature and try to understand what's going on. And some of these topics, as I've said, are really researchy things and cutting edge stuff. And so it's not far-fetched to say that we'll learn much more about dimming in the future. Now, the postscript is, could we detect, I think many of you know Martin Hendry from Glasgow. He's a great outreach kind of person, gives wonderful public lectures, and knows all about LIGO, which is the gravitational wave observatory, which has just in the last couple of years succeeded in seeing these coalescing black holes. So it takes a whopping, monstrous, massive kind of thing out there in deep space to produce these bright enough gravitational wave signature. So the question is, would Betelgeuse be detectable? So I asked Martin this morning, and his answer was quite clear: maybe. And so the answer turns on an unknown. The question is, does a supernova happen isotropically? Is it just a point explosion, so it goes off in all directions simultaneously? Or does it happen in a asymmetric way, so that there's some elongation, some focus, some preferred direction of emission? That's important, because gravitational waves don't get excited by a monopole, which is a point explosion. They have to have a dipole term, a quadrupole term, really. And so we don't know enough about the mechanics of supernova explosions to be able to say. Martin said he thinks there are models that will predict that we can see it, but it would be great if it happened and we could see it. So thank you very much.
That's great, Hugh. Thanks, Art, for that. Really interesting. And I say, so you've been talking to Martin. He's a great friend of Sigma. He's been up many, many times. And I would say there that his answer maybe is probably meaning nobody knows. Is that
I think I paraphrased. He gave me a very articulate answer. As you know, he's a sagacious person, but I think maybe sums it up pretty well.
Yeah, see, he's actually retired now as well, I think, hasn't he? I think, did I read that? Or he's
no, he's a step down from being the head of school.
That's right, yeah. Yeah, you're not traveling around quite so much, I see him saying that.
He's very active, and he's, of course, he's hard to hold back. He does so much.
Oh, yeah, he's been up to see us many, many times.
Yeah.
A great speaker. I think there's a couple of questions. Is there, Donna?
There is indeed, yeah. Bear with me 1 second. I'm just trying to, well, I can't, have I got you in my, I'm not muted, that's okay.
No, you're right, you're fine.
Sorry, trying to juggle looking at the questions and my camera at the same time. Right, Bill Graham is asking, point of interest, when you say Betelgeuse could explode any time, as it is 640 light years away, we may not see it in our lifetimes. Of course, it might have happened 639 years ago.
That's right. That's right. It could be tomorrow, which means it happened 600 years ago.
that we might see it tomorrow.
Which would be brilliant. And Gordon said, fascinating talk, Hugh, thank you. Can you explain how it takes more than 10 days for the Betelgeuse supernova explosion to reach maximum brightness?
No, but it's roughly speaking, I suppose it is because the reason a star has a certain brightness is because of its size, right? It's a black body emitter, and so it's the amount of radiation you get from it is dictated by its size. So the photosphere, where is the photosphere relative to the center of the star? And as a supernova happens, the photosphere expands. The star it's very hot, and so the actual physical size of the object gets larger and larger, and that happens very rapidly because it's expanding. So I think that's probably the main factor in the increase of brightness, but I wouldn't know how to estimate the timescale for that. And it's eventually, of course, the ejection of the supernova gets detached, and so it gets faint, and that would be this part over here, I think. So it's no longer optically thick. Is that roughly helpful?
I think so. I think, well, that's the only questions that have come up, apart from the ones that we asked during the talk. So.
Okay, Donna, thank you very much. We'll just end that there. We want to just give a big thank you to Hugh for coming up. Now, you came up not long ago, and we always give you a little gift, don't we, when you come up. So we're going to have to send this down to you this time.
That's too bad. I would like to come up.
You definitely, once we get this sorted, you can bring Lindsay up. For those of you who don't know, Lindsay Fletcher, who was in as an attendee, is actually Hugh's wife. She's been in spoke to Sigma many times, and when we were on having a practice session the other Sunday, she said she'd be more than happy to do a talk for us again. So I'm sure Donna will be in touch very, very soon to get you organized for that. Okay, but I say we'd like to give you a little gift. It doesn't show it very well here. Oh, I've got it. Yep.
I have one just like that.
You've got one. It may not be quite like that, because I say we always say if you get 6, you can change them in for the decanter.
And after 20 years in Scotland, I know what to do with it. You put it in some whiskey.
So you've probably got 2. I think Lindsay's probably got 2. So that would be 5. But they are different designs. They've got to be all the same design if you want the decanter. Okay. No. But I say, I think I've got your address. I'll get this in the post to you as a thank you. And,
thank you. Thank you.
And then we will get you both back up here one day and take you for a meal and have a drink, maybe, but once this silliness is over with. So as I say, that was a great talk. All the questions are done. We'll take a quick 10-minute break just to reset everything for the second half. In the second half, as I say, we'll have Stuart will be doing his space news. Mick will be giving us a guide around the sky at the morning sky at night. I'm going to do a little bit of club news. Now, you want to hang on for the second half, because if you haven't read the newsletter yet, in the club news, there's going to be a little bit about the Sigma Christmas quiz. We're going to try and do a Christmas quiz. Okay. But you'll have to hang on and come back to us in about 10 minutes' time. So we'll come back at, let's say, 10 to 9. Okay. So we'll have a quick break now.
Same link here.
Just stay here for this one, yep. I'll explain all about the gathering and that after the second half, okay? In the second half. All righty. So let's go and have a comfort break. We'll see you all later. And welcome back, everybody, to the second half of the Sigma October meeting. Right, to say we'll kick off now with Stuart and his space news. So over to you, Stuart. Hello, Stuart. Are you there? You're still muted, I think.
Is it still muted, am I?
Yeah, and your video needs to come on as well, mate.
Sorry, let me just stop that. I've lost the controls gone. Just bear with me.
Okay. As I said, we've been having a few technical issues tonight, and it's just par for the course. It would not be Sigma if we didn't have a couple of technical issues.
Right. Right. Is that better?
I can see you now. That's it.
Okay. Right. I'll start again.
It was looking so smooth and so good, but there we go.
I'll have to run all these back to the start.
You need to share your screen again.
Yeah. Right, start again.
There we go.
Okay,
Perfect.
welcome everyone, and welcome to October Space News. I've selected a few items from the news. Some of you may be well aware of them because there are a lot of items are now and topics are appearing in the newspapers, and there may be updates to some of what I've put down there. But let's proceed. SpaceX, Elon Musk again is in the news, and his SN6, serial number 6 of his Starship, performed again successfully, going up to 500 feet, and it's forming part of his full-size Starship for the Mars colonizing vehicle. The test flight was similar to one conducted last month by SN5, and both vehicles met the same altitude and moved the same short distance laterally from the launch. But Elon Musk said this time this one was a lot smoother and a lot faster in operation. SpaceX is developing the 165-foot tall Starship and a giant companion rocket called Super Heavy. And these will take people and payloads to the moon, Mars, and other distant destinations. Both are to be reusable, rapidly reusable, he says, and Super Heavy will be needed to get Starship off Earth. But the passenger craft will be able to launch itself from the moon and from Mars. And there's a picture of the Starship doing its prototype test. Now, what I'll do, if you give me a few seconds, I will show you a short clip. Share screen. Oops. Okay, so that's the launch up to 150 feet. The SN5, the previous one, and the SN6 is powered by one of the Raptor motors that they've generated or produced, and it's an atmosphere motor. The next version, 7 and 8, will probably use 3 Raptors for the test. The final Starliner, or Starship, sorry, will use 6, three of which will be atmosphere motors, and 3 which will be vacuum motors for interspace operations. The Super Heavy will use 30 Raptors, and that's what's needed to get the Starship off Earth and on its way to the Moon and Mars as appropriate. I'll next look at what the Chinese are doing. Now, China became the third country ever to launch a human into space in 2003 and has been expanding its space program ever since, and regular rocket launches are now taking place. And these, in a way, are trying to mirror what the Americans are doing and try and catch up with the Americans. On the 4th of September, they launched a Long March 2F rocket. And after 2 days in space, according to state media, it returned to Earth, making a safe landing. China has reported very few details about what the spacecraft did or what it was planned to do, but it's believed it may have deployed a satellite while in orbit. No images of the spacecraft nor the launch have so far been released. An apparent higher than usual level of security surrounding the mission also prevented bystander images appearing on social media. This is a picture of in October 2016 of the same Long March 2F rocket that launched on the 4th of September. It is believed the launch is linked to China's plans to, over the past few years, to build and operate a reusable space plane, although that connection has not yet been confirmed. Again, on the 7th of September, the Chinese Long March 4B rocket was launched with a new Earth-watching satellite. The satellite was the powerful Gaofen 11 issue 2 Earth observation satellite, an optical observation satellite capable of returning high-resolution images showing features smaller than 3 feet across. And here's the launch of the Long March 4B with the Gaofen 11 satellite. Data returned by the Gaofen satellite will be mainly used for land surveys, city planning, land rights confirmation, road network design, crop yield estimation, and disaster prevention and mitigation, according to the Chinese media. It will also offer information to support the belt and road construction, according to Xinhua. It will join a larger suite of Gaofen and other Earth observing satellites as part of the China High Resolution. And the belt and road construction is China's actually producing a seaway, railway and road structure across the whole country. However, as on previous occasions from the inland launch sites, and this was from the desert in the north, the booster spent first stage narrowly missed a school when it fell back to Earth, witnessed by the videos. Now, again, I'll try and show you. This, you can see the rocket, the first stage, falling back down to Earth. And that's where it hit the ground close to a school. And you can see the wreckage here. You can actually see people down there sorting through the wreckage. And that's the smoke, orange smoke in the distance. The reporter from the Weibo, which is their media site, said you could hear the children screaming and talking as it came down. And the propellant for the first stage was a mix of toxic hydrazine and nitrogen tetroxide. So contact with that could cause serious effects on health. So there was a lot of concern, but they weren't quite sure whether people were warned beforehand, because there was a lot of people out watching when that happened. But it's interesting that it seems to be a regular occurrence from the inland launch sites. This was the 25th launch so far in 2020 for China, and China's main state-owned space contractor stated in January it would aim for around 40 launches in 2020. So there's still quite a lot of activity to take place. Now, another subject I was planning to look at is the astronaut muscle and bone wasting, which I'm not sure whether you're aware of. A major challenge astronauts face during prolonged space missions is the simultaneous loss of bone and muscle, which weaken and atrophy during disuse outside the constant pull of Earth's gravity. Early research has found that in microgravity, astronauts can lose up to 20% of their muscle mass in less than 2 weeks. In the weightlessness of space, muscles aren't needed to support the body, and astronauts' muscles start to adapt to that change almost immediately. Instead of maintaining the usual base of muscle mass needed for a life on Earth, astronauts' bodies quickly get to work ridding themselves of unnecessary tissue. And although this might be ideal in space, it's problematic once back on Earth. And astronauts have to exercise for 2 hours a day on the space station just to maintain a healthy amount of muscle mass that will need once they're back on Earth. And they have, I understand, 2 fixed bicycles and track runners on the station for keeping fit, keeping their muscles up to standard. Yet in the 1990s, a husband and wife team of C. Jean Lee and Emily Germain Lee believed they had found a way to fight this bone muscle loss, when Lee and his colleagues at Johns Hopkins University helped discover myostatin, a protein that normally limits muscle growth. They showed that mice in which the myostatin gene was deleted had a dramatic increases in muscle mass throughout the body, with individual muscles growing to about twice the normal size. Lee then went on to suggest the possibility that blocking myostatin might be an effective strategy to combat muscle loss due to a wide range of diseases. And they produced their findings in the Proceedings of the National Academy of Sciences. Now here you see the mice. The larger mice are those without the myostatin, where it's been deleted, and you see how much they've grown compared to the normal mice, which is the smaller ones. And for the past 20 years, the researchers have wanted to see what effects blocking myostatin would have in mice sent to space. They finally got the opportunity to do so in December last year, and 40 mice were launched from NASA's Kennedy Space Center to the ISS aboard a SpaceX CRS-19 cargo supply services mission. 24 of the 40 mice were normal. 8 of the 40 mice were missing the myostatin gene. 8 others were treated with a molecule that suppressed both myostatin and a protein known as activin A. And activin A has a similar effect as on the muscles as myostatin. It was found that normal mice lost significant muscle and bone mass during the 33 days spent in microgravity. Mice missing the myostatin gene and with a muscle mass about twice that of a regular mouse largely retained their muscles during space flight. And you can see here in the 2 center rows, the untreated mice on the ground and in flight. And you can see that the reduction in the bone after the activity. We'll look at other astronaut implications in space, but just to mention on the mice, it doesn't necessarily mean that it's going to be the same with the humans, as although according to Robbie Burns, there are similarities between mice and men, but I think they need to do some further trials and tests on astronauts to see what the impact is before they start doing any serious testing. Other astronaut issues are height. Over a 6-month period on the ISS, astronauts gain height of about 3% because of their vertebrae extend. And this continues 2 or 3 months after they return to Earth before it settles back to its normal length. And also on Earth, because of the gravity, all the fluids tend to fall down to the lower legs and reduce from the head and the upper body. In space, with microgravity, it tends to level out. So the astronauts tend to get puffy faces for a period once they get into the ISS, and that then generally comes back to normal. There's also, on return to Earth, they become disorientated. They forget the fact that if they let something go, it doesn't stay there. They tend to go around dropping things. That's an issue which takes a little while to overcome. And also, while they're in the ISS, they get difficulty sleeping sometimes because of the flashing of light from the cosmic rays, which actually penetrate and go through, and some of them have difficulty over the whole period in terms of sleeping. The next one I was going to look at is the Russian S-7C launch. On the 21st of September, Rocket Science News, spacetravel.com, reported that the Russian State Space Corporation, Roscosmos, has commissioned an economic assessment of whether operations can be resumed on the floating spaceport sea launch, now owned by the S7 Airspace Corporation, with a return to planned launches in 2024. The technology and research company that is part of S7 Airspace Corporation, which owns the sea launch floating spaceport, has also begun work to develop a light launch vehicle with a reversible first stage. This again is looking at what Elon Musk is doing with his recovery ships by launching and recovering at sea. And that was set up in 1995 with a combination of Russia, the US, Ukraine and Norway. And they did about 3 dozen launches, which were commercial launches from this seaport. But in 2014, they abandoned it, and all the US and Ukraine parts that were on it were sent off to Russia, and they then put it to one side. But they've now brought it out again. A7 bought it over, which is an airline and technology company, and they're planning to open it up again. And that's one of the launches back in between 1998 and 2014. It drops down, sits on 2 floats. It has its own power. It's got 4 propellers, fore and aft, and it gets in position and settles down in the water by about 21.5 meters to give it a very firm base. And its position is within 1 degree for launching. So I see that will be coming up shortly again in the news on what they're trying to achieve there. Launch operations are carried out from a steady platform. Launch platform moves on a couple of large pontoons as a self-moving by a 4-propeller propulsion system, which has got 2 propellers on in each case. As soon as the launch point is reached, the pontoons are lowered up to a depth of 21.5 meters to achieve the steady launch position, which the horizontal position of the platform is provided with an accuracy within about 1 degree. And I'll then go on to the lunar flashlight. And you may well have heard of the Artemis program. NASA is moving ahead with Artemis, whose goal is to land the first woman and next man at the moon's south pole by 2024. When humans return to the moon this time, they'll likely stay longer than their Apollo counterparts in the late 1960s and 70s. The record stay during the Apollo missions was about 75 hours. To accomplish these future longer stays on the moon, lunar astronauts might utilize some natural resources from the moon itself, in particular water, ice said to have been confirmed to exist in 2018 in the deeply shadowed craters at the moon's poles. And this ice can be melted and purified for drinking, and it can also be used for rocket fuel. And to achieve this, NASA's Jet Propulsion Laboratory set up a project called Lunar Flashlight, which is a CubeSat with a projected launch date of 2021 and a specific mission of detecting naturally occurring surface ice in the shadowed craters on the moon. And that was reported back in April in the IEEE Aerospace and Electronics magazine, Systems magazine. And that's a artist's concept showing the lunar flashlight using its laser to identify water. And that's another shot from above looking down on the lunar flashlight. And finally, we end up with some ISS news. On the 23rd of September, the astronauts in the ISS were forced to take shelter as the ISS was urgently moved to avoid space debris. The crew sealed themselves in an attached Soyuz spacecraft in case they had to abandon the station. And the thrusters of a Russian Progress cargo spacecraft were fired for 2.5 minutes to push the ISS from the path of a piece of 2018 Japanese rocket that broke up last year. And NASA stated that the ISS had to maneuver 3 times in 2020 to avoid debris. And in the last 2 weeks, there have been 3 potential high-risk conjunctions. And the ISS had to avoid bands of debris 25 times between 1999 and 2018. And I think we mentioned on previous space news, the debris is getting worse at the low level. And according to NASA, the ISS is moved if the chance of collision is above 1 in 10,000. However, there is some good news. The multi-million-dollar space toilet, officially known as the Universal Waste Management System, is NASA's latest upgrade on in-space commode based on astronaut inputs. The new toilet is completely self-contained, making it easier to repair than old models, and is 65% smaller and 40% lighter than the one currently on the space station. And the new toilet may eventually be used in crewed missions to the moon or Mars, but astronauts on the ISS need to test it for 3 years first to make sure it's durable enough for long interplanetary trips. And I understand they're actually fixing it right next to the old one, so there'll be the choice of 2 toilets to use. But that's the new toilet. So if anyone's looking at that and think, well, that would go well in the garden shed, the cost to build is more than $23 million. Cheap at twice the price, I would have thought. And that's it. Thank you.
Okay.
If you have any questions, I'm sure Donna will be pleased to answer them.
Okay, Stuart, that was brilliant again. Universal Waste Management System, I like that. Yeah, that's a long name for what that actually is, isn't it?
I've lost you, Pete.
You've lost me? Can you hear me now?
I got you, yeah.
Yeah, okay. Let's say we're having a few technical issues at this end. I think my Wi-Fi is playing up a bit. Okay, I don't think there's any questions there. I cannot see any come up in. So what we'll do now is we'll head straight over to Mick, if you're ready.
Thanks. Yeah, thanks very much, Pete. Okay, I'll just share my screen here and find where don't need any sound.
Yeah, we got that.
So, you got it? Yeah, okay, cool. Hi, folks, and welcome to the October edition of Sigma's Murray Sky at Night. So first of all, let's have a little look at the planets and see what they're up to. So across the horizon through this month, we should be able to see 5 out of our 7 neighbouring planets with relative ease. Mars is going to be in opposition next month, giving us the best viewing times, and its dark surface features should easily be resolved with a small telescope. So looking first here, just to see some close passes that we can get out and take snaps of. Tomorrow morning, 3:30ish, you can see there, Mars is going to be within 0.7 degrees of the moon. Moving forward to the 13th, a bit later, and I want to be east. So on the 13th, you can see the moon here is close to Regulus, and Venus. You have to be up out your bed early to catch this one. And then over the next couple of nights, it'll be the 14th, it'll be closer to Venus, and then moving past. And as I say, Mars is going to be opposition actually at 2300 on the 13th. Not that I really need to go to that sort of time, but that's going to be a good opportunity this month to have a look at Mars. So moving on to the 21st, we have the peak of the Orionids meteor shower. So the Orionids can be found between Orion, between Betelgeuse and, I'll zoom out a little bit. Oh, wait. So the peak of it can be found between Orion and Gemini, the twins. So here we have Castor and Pollux. I'll just put on the line so you can see the constellation and Orion there. So that should be pretty easy to find. The radiant is going to be round about here. So if you look 20-30 degrees all around, that's where you should be able to spot meteors. It's going to be a nice dark night for these this year for us, thankfully, because the moon's going to be set by 7 o'clock on the 20th, and it doesn't come up again until the afternoon of the 21st. So it's going to be a nice dark night. So we should be able to hopefully get some photos of some good meteors there. Later on the 21st, what time am I looking at? 7 o'clock. So 19. Right, I'll take it back a little bit. So this is another close pass. So on the 21st, we'll get the moon close to Jupiter and Saturn there, just before they set. And then the 22nd, will be there, 23rd. So another photo opportunity. Of course, the next thing that happens will be the 25th, Sunday the 25th. British summertime is going to end. And we'll be back to GMT, definitely start of the winter hours. On the 29th, what was I looking at? Yeah, Mars is going to be within 3 degrees of the moon. So there's another opportunity for you. And then on the 31st, Uranus is going to be at its best place this year. It comes into opposition on the 31st at 4 o'clock. So later on that evening, if you put a small telescope on it, you should be able to pick out its green-blue globe. Pretty sure, unless you've got a massive telescope, you won't be able to see any of these moons. And funnily enough, this planet hasn't been this well placed in the northern sky since the 1960s, apparently. So when it comes into opposition, then it's a really good chance to have a look at it, because you might not get another chance for a good while. So that's the planets. Let's now go and have a look at some deep sky objects. So as I mentioned in the newsletter, the Great Square of Pegasus dominates the southern sky. And I covered a selection of deep space objects within Pegasus and around Pegasus last month. So this month, what I'm going to do is have a look at let me just put some constellation lines so I find things. Let me just zoom out a little bit. So we'll find the Great Square of Pegasus, which I can't. Wait. Of course, I've got this set to find my way around here. Give me just a second, let me get the... This is what fine all day when I was practicing. I think the gremlins have moved in here. Right, there we go, right in front of me, look. So, we have the great square of Pegasus here. And what I'm going to do this month is cover its neighbour, its easterly neighbour, Andromeda. So I'm just going to put the boundaries up of the constellations, and you can see I'll put the lines back on actually as well. So you can see the area here that's covered by Pegasus. It's pretty massive at 1220 odd square degrees. Andromeda, its next door neighbour, has got quite a large area as well, but it's only about 720 square degrees. So to find Andromeda, as you can see, I've marked Alpheratz here in the top left corner of Pegasus, great square. We'll use that to start finding Andromeda. So moving to the east. Now, unfortunately, Stellarium doesn't paint the whole picture of Andromeda, so that's the reason I added it to the newsletter this month. So if you've got that to hand, otherwise, if you can follow me in your head, I'll try and point out all the constellation. So this going across the southern edge, moving east, we got Delta, Andromeda, then Mirach, and then Almach. And then there's also a northerly arm that goes up through Pi Andromeda, Sigma Andromeda, and then if you follow up to these three stars here, we have Iota, Kappa, and Lambda Andromeda. And then it moves further up here to, wrong one, hold on. Oh, I'm sure that was the right one. That's the one there, Omicron. I thought it was closer to the border. Ah, there's a border because I took them away. That's what threw me. Right. So there's also another arm of Andromeda which goes from Mirach up through Mu to Nu, and then moving to the east up to Phi, and then across to 51 Andromeda. So you've got like a leg going across here. So we've got that one going north, and there's also another little leg going south through Epsilon, Zeta, and Eta down here. Where am I at? So the majority of Andromeda is circumpolar. It never sets from the UK. And on September evening, circumpolar M31, which I'll talk about in a moment, which lies roughly at the centre of Andromeda, is well up in the eastern sky by 9 o'clock. And it's going to culminate in a very healthy 80 degrees or so. So right above you, easy to find. So how do you find M31? So M31, as we all know, Andromeda Galaxy, we come from Mirach up through Mu, and about the same distance again, just here we'll find Andromeda Galaxy. So this, it's an easy naked eye target on a haze-free moonless night. If you have any light pollution, kind of forget it, it'll just blend into all the muck. So it's a hugely impressive local group galaxy at a distance of 2.5 million light years, and one of the Milky Way's closest companions. And it's probably the finest deep sky object in the northern sky. So as you look round M31, you'll notice that there's a couple of other fuzzies, which are pretty close proximity. Down here we have M32, which is a little bit closer than 2.5 million light years, not a lot. And further up to the north we have M110 NGC 205. So M32 is a dwarf early type galaxy, large and bright elliptical galaxy, and as you can see, it's immersed in all the bright outlying regions to the south of M31. So just half a degree to the north, we have NGC, I'll say NGC 205 for a reason. So this is a relatively rare compact dwarf elliptical galaxy, the largest of M31's companions. And as I said, it's slightly further away. And its actual size equates to 16,000 light years, and it weighs around 10 billion solar masses. So this was discovered by Charles Messier in 1773, but he didn't include it in his famous Messier catalogue. And it wasn't until 1967, so almost 200 years later, the NGC 205 was actually added as the last entry in Messier catalogue as M110. So a small telescope shows M110 as a smooth southeast to north-northwest orientated oval, perhaps weakly concentrated towards the centre, and it's a bit harder to see than M32, owing to being afflicted with a low surface brightness. So the next one on our little tour, we don't have to go too far. If we come back down to Mirach and stick a telescope on there and zoom in, just to the north you can see a little fuzzy patch. This is, come on Stellarium, NGC 404, Mirach's ghost. So 10th magnitude, and it lies around 10 million light years distant. And it's a prime example of a lenticular galaxy that's presented face on. I don't think it's shown particularly well here, but I've never actually looked at it myself. So galaxies in its class are disc-shaped with little ongoing star formation, and they show no spiral arms. If you're making a list of galaxies that are easy to locate, which this one seems to be, but hard to observe, then this one would probably be quite close to the top of the list. The clue to this contradiction is in its name, Mirach's ghost, because its overpowering glare can cause internal reflections and artifacts when you look at it through your from Mirach. Sorry, yeah, the glare from Mirach can give you some reflections in your eyepiece. So the best way to try and view it is get it as close to the center of your eyepiece as you can, up the power, so you're reducing your field of view, and then try and nudge it so that Mirach is out the way to get a good look at it, NGC 404. The next one we're going to look at is up in the further up to the north. So the way to find this, back to Delta again, which is between Mirach and Alpheratz, up to Pi, up to Omega, up to these three stars. So once we get to here, we want to start looking towards Omicron up here. And this star that's about a third of the way along, let me get that centered and zoom in. Now let's see if I can find this. It was a little bit tricky earlier. Right, I think I've got it. So if you come down from 13 Andromeda to this star, and just here, sure that was it. Right, I'm going to cheat a little bit. Oh, just off. This is Copeland's blue snowball. NGC 7662. A beautiful blue snowball planetary nebula. Now, I'll try to zoom out, but not too far for the next one, because if we get 13 Andromeda again, it seems to be oriented. Yeah, okay, that's. So if we come about 5 times the distance, same direction, past this big star here, V385 Andromeda, we will find our next target, NGC 7640, a spiral galaxy. At a magnitude of 10.8, it's 36 million light years away. And it's presented, as you can see, highly inclined to a vantage point along its north-south orientated 11 arc-minute long axis. I'm going to tell you about that. So it's quite a tough object for small to moderate telescopes, despite its favourable edge-on presentation, given more light from the centre, from its core. But a 4-inch telescope should show under good conditions. If you jump up to an 8-inch telescope, you should be able to see virtually edge-on object with narrow, even velocity, nebulosity, sorry, and a bright bulge at the nucleus position. So moving on from there, we go to our last one, which is across the other side. So back to Mirach again, and I'll get rid of this. Right. So heading east from Mirach to Almach, you pick the next brightest star to the east, and then head directly down to this one. I'll zoom in a little bit, a lot in fact. And then coming up to the left and straight up, you will find this. I need to select this because if I'm not in the circle, it doesn't select it. So this is NGC 891, a much celebrated edge-on spiral galaxy. So it comfortably takes its place in the pantheon of those special edge-on galaxies and is arguably the finest inclined spiral visible in the open sky. It lies around 30 million light years distant. It's a very attractive proposition for amateur imagers, with deep images easily capturing the prominent obscuring lane of dust that you can see here, an interstellar gas that runs along the entirety of its 13.5 arc-minute axis, although it doesn't really have a prominent bulge. Should be. So even though it's shining at a relatively bright magnitude of 10, plus 10, on a transparent and moonless night, you'll probably need a 4-inch telescope, and that's only going to spot it as a needle-like sliver of light. You'll need probably a 12-inch telescope if you want to glimpse this fine dust lane. And that's all from me for this month.
That was brilliant, Mick. Thank you very much. Now, we'll admit that last galaxy you showed there, I wasn't seeing it, and it is a stunner. It really is. Yeah, I've actually imaged it. I remember right. It's quite easy to find. Quite easy to find. Okay, if you want to just stop your share, I was going to move on to the news. There's no questions I was going to say, Mick, so we can crack on. I was going to move on to the club news, but what I'm going to do first is going to bring in Eric Walker, who's going to tell us about a new exciting project that he's actually working on. I'll ask him to start his video. Are you there, Eric?
I am here, Pete. You can hear me okay?
How are you doing?
I'm doing very well, thank you very much.
Okay, over to you then. You can tell us all about what you're being up to. I've been watching it, and it looks complicated, but go on.
Well, thank you very much for inviting me. I'm glad you didn't give me any pre-warning of this. So I've decided not to have another glass of lager while I'm doing this. Yeah, the with the COVID situation, you know, we've all, I think, adapted very well, all our astronomy clubs and groups, to using Zoom to have our monthly meetings and such like. However, we're all practical observing clubs. And the one thing we were all concerned about was missing out on the ability to carry out and host public observance sessions. Now, at the tail end of last observance season, what we did at Highlands Astronomical Society is we managed to hook up a high-spec, high-resolution astro camera, and were able to take live images of the night sky and beam them into the Warm Room so that people could watch the images in the comfort of our Warm Room in the observatory. That also enabled people with disabilities or limited ability to come and visit us. However, as we know, everything changed rapidly. So what we have done is we have expanded on the technique that we proved would work, and we are now able to carry out live webcasts of observation sessions at any time. I happen to have this set up in my observatory in my back garden. I'm working with a small team in Haas, and I'm just about to have discussions, Pete, with a few of your guys, Mick and Rich, and hopefully yourself, about sharing the tech support resource in order that we can, from the north of Scotland, deliver a program of live observing webcasts to all our members and to our guests and to the general public, local and worldwide. I also believe Cairn Gorham Astronomy Group are doing something similar, and I think I saw Sam in the chat earlier on, so it'd be great if he, if I was able to have a chat with him as well. We had a test session on the 23rd of September. 12 devices were hooked up to that, and we carried out a very successful session and learned a lot about it. What I'm going to do is give you a link. So if you want to have a look and see the outcome of that, I've put it in chat. Click on that and it'll take you to the YouTube recording of that session. It's warts and all. It's a bit like Cromwell. Helen from Sigma says, "Is that a bit like Slew?" Kind of.
One man slew though.
But it is. It's amazing. It's amazing, Helen. We were able to see the color and structure of M57, the Ring Nebula, the Dumbbell Apple Core Nebula, M27. We were looking at the core, the dust clouds of M31, the Andromeda Galaxy, which Mick just showed us there. It's an absolutely wonderful system. There are little technical issues that we're working rapidly on overcoming. All you need to be able to join us is a YouTube channel. If you want to take part in viewing it and in the live chat, and the live chat is fun. You can type in your comments, queries, requests, banter, and it really is. It's good fun, but you need to set up a YouTube channel with that. I've sent my members a way of doing that. Pete, you could. I think you've probably got the same thing that you could possibly distribute.
Just make a like one club account and everyone can join into it, sort of thing.
Yeah. Well, I've set up. I've set up a Haas channel, which actually I shall just cut and paste that into chat for you as well.
Yeah, to say Caithness are, that's not Caithness, sorry. Cairngorms are doing one Wednesday night. We're working in the background with them to bring
Cool.
that on. I'll just say that while you're setting that up, just in case that the link I sent out to you for that for Wednesday will change the YouTube link. Because I say we've had some gremlins major here tonight, and the YouTube's gone totally
Belly up.
upside down. Okay, so
Yeah.
it'll be a new link going out for that one. I'll be talking to Sam later on about that.
Yeah. So I am very confident that the North of Scotland astronomy groups are going to be able to carry out and share live observing webcasts over the season. It'd be great if there was several clubs could do this, because then that reduces the risk of weather, shorting out, one area. It means somebody else might be able to pick it up, and it also spreads the resource across the groups and clubs. But that's for further discussion. But
Sure.
Those two links anyway should let you see what we're doing. We will be webcasting as soon as possible. Once the moon dies down a bit and the weather improves, I would anticipate we should have a live observing webcast going back end of next week. So say about a week today, roughly.
That's brilliant, Eric. We're
okay,
all going to look forward to that, I'm sure.
Excellent, Pete. I'll
We'll
shut down now.
and we'll see what we can do to help you out. Thanks very much, Eric.
Thank you very much.
Brilliant. Okay, right. So I'll just move on to club news. I won't keep you too long. As I say, so we're going to go with the gathering after this one. As I say, yeah, we've had a few gremlins, and also some people have been having trouble getting on tonight. There seemed to be the link in the newsletter. I'm not sure what's going on. I tested it because I sent it to myself, and I tested it, and it seemed to be working fine. I put all the links in the newsletter to try and cut down on the number of emails you're getting. But obviously it's something going wrong. So what I might do, if everyone's okay with it, I'll start sending them back out. Well, what I'll do is I'll send the link in the email along with the newsletter. Okay, so you've got two options. If it isn't working in the newsletter, you can just click it straight from the email link that the newsletter comes with. I'll try and sort this out as we can. But say it wouldn't be Sigma if we didn't have some sort of gremlin going on. At least there's no sort of projector screen falling over and attacking our speakers anymore. That doesn't happen when we're here. Well, not unless you're watching it on a big widescreen TV and that's fell off the wall and hit you. I don't know, maybe it has. Yeah, so as I say, the member Zoom gathering is going to happen straight after this. Okay, the reason we're doing this is because Sigma has always been a very social club. And I say the one thing we want to try and get back in to it is that social side of things. We thought by this time we would be getting back in the hall and we'd all be having a cup of tea and standing outside looking at the stars, but obviously that's not going to happen. So Rich did actually put the link in the chat earlier. I think he's going to do it probably again now, Rich. That'd be a good idea if you do. You can copy it. It should be clickable. You can click into it, but don't do it just yet. So if everyone else could stop putting stuff in the chat and just let Rich put that one in the last. So when I finish, click that link and it should take you to the waiting room for the next meeting. As I say, what we're doing this for, as I say, to get us all back together, but we are planning to try and run a Christmas quiz. Kevin's working busy in the background, trying to suss out how we can do this, because with the meeting side, this is why we got to do it on a separate stream and not on here. On the meeting side of Zoom, you can have individual tables. So the early thoughts are, we got to try it out first, is we'll set you all into individual rooms around the table. One of you will be in charge of that table, and we will email you out the questions of every round. Okay, that's the thought so far, but as I say, we've got to try and practice it and make sure it works. But doing this gathering afterwards is going to give us an idea of how it might go. We haven't got tables tonight, we just have a good chat and a good natter, and I'm going to get a whiskey because I need one after tonight. So join me if you will. As I say, like I said in the newsletter, you don't have to have your video on if you don't want to. I know it makes some people feel quite uncomfortable. It took me a lot of getting used to do this online when I'm looking myself in the face back in my screen. It's unusual. Obviously, if you want to chat, you will need your microphone on, but we're all friends. It's only like, if we were in a cafe having a cup of coffee and a cup of tea, looking at each other and having a chat. Okay. Sigma on YouTube, obviously. Anyone who's missed any of I know a couple of you missed the beginning of the talk that Hugh did. Our YouTube channel is up and running. From now on until I don't know when, we're going to put the links up as unlisted. So they'll only be available to members. So if you did miss anything tonight, or if you want to watch it again, ping me an email and I'll send you the link to the link on YouTube. Okay, I will send each month's YouTube link out in the following month's sort of newsletter as well. Okay. Observing nights obviously on hold, as Eric says, we just can't do it at the moment. Remember to invite a friend. So we are very lucky. I think we've got another new member wanting to join, which is really, really good. And Nick told me the other day, membership forms have been sent out. But if you know of anyone who's interested in astronomy, just let them know we're here. Send me their email, or I can sort of send you the link for them to come and join the meeting. You know, as a friend of a member, you get your first meeting free. As I say, the weekly how-to meetings, I'm trying to get that back up and running, but obviously there's not an awful lot going on anyway. So with Eric doing his live streams, I say the Cairngorms are doing a live stream of Mars. That's Sam, who's going to be the telescope operator for that on Wednesday night. And like I say, there was a problem with YouTube tonight. Don't use the link I sent you the other night because it ain't going to work anymore because it's already been run and gone. I will set up another one and I'll send that link out to you. Okay, and that'll be Wednesday night and it's on at 8 o'clock. Okay, so hopefully we'll get a live stream of Mars. If not, there's a backup talk as well. So come along, let's support each other here. The outreach side of stuff, as I say, obviously I haven't done much, but I've been approached by a member of my family, my nephew in fact, and his son goes to one of the Cubs down there and they're doing their astronomy badge, and I said, well, why don't you let me do a Zoom presentation for them, because obviously they can't have anyone coming and visiting. So the outreach is going again. Okay, it may be a bit distant going down in Gloucestershire, but we're going and putting our face out there. And don't forget, if you've got anything from me, just ping me an email, pick up the phone, give me a ring, and see what we can do, or just tell me in about 10 minutes time when we're in the gathering. So the next meeting is Ice Giants by Pauline McRae. If you've never seen one of Pauline's talks, definitely come along. She's a fantastic speaker, and I'm sure this was going to be no different. So with that, I want to thank Hugh for his wonderful talk, and hopefully, as I say, we'll get you up here again one day along with Lindsay and all gather together. Donna for handling the Q&As and doing it very, very well and very, very professionally within the talk and at the end. Stuart for your space news, for getting through it with a cold. You said you hope it's a cold, and we all hope it's just a cold. Mick for space news, sorry, for the Sky Night, and Richard, thanks for being in the background as the Zoom host, because I say a lot goes on in the background. And for all your good selves for coming along tonight and supporting your local astronomy club and other astronomy clubs in the area. So that link is now in the chat. If you want to click that now, you probably can do it. It'll take you to a waiting room. You'll have to leave this meeting probably first, but it'll take you to the meeting room, waiting room there for that meeting. And I will say good night and thank you all very much for coming along. And I will end this now, and we'll see you in about 5 minutes. Good night, everybody.